right. Well, we're here, magnetism, getting quite far this semester, I think. And it's a really interesting topic. I'd like to start by asking if anyone, does anyone know how a magnetic field is created? Do you have any idea what causes a magnetic field? Where did it come from? Hassenpreet. How do you get a magnetic field? Hassenpreet, are you there?
Yeah, yeah.
So,
Is it because they have north and south magnetic fields have north and south poles, so when opposites meet, it creates like a magnetic field? Is that how that works?
well, for a bar magnet, yeah, can they do? There is an idea of poles or really any magnetic field. Yeah, that's true. But in order for a magnetic field to have a pole, it has to already be there. What I'm asking is, how does it get there? Any idea? Now, that Dami says when the metal is electrified. Well, what do you mean by electrified, Dami?
Um, when electricity is um, supplied to a metal for a long period of time.
Okay, that's not such a bad answer. Yeah. So, what happens when electricity is applied? What does that refer to when electricity is applied? Like, I mean, the context, because we know, I mean, we just spent time doing that. Like, you mean like in the context of circuits? That's what you're referring to?
Yes, okay.
Okay. Well, yeah, that actually is one way that it will happen, applying a voltage to a basically current, causing current to run in a wire. That's true. That is one way in which it's caused. I guess I want to go with a little bit more basic answer. And essentially, anytime a charge moves in any way, the motion of charge causes magnetism. And charges can move in one of three ways, basic ways we studied in terms of kinematics. You can have translational motion, which is what essentially you're saying for current, because we talked about what causes current from a microscopic level, right? It's drift velocity. Whenever you apply a voltage to a wire, and we said that the current is equal to the magnitude of the current, magnitude of the charge times the charge density times the cross-sectional area times the drift velocity. So yeah, translational motion will cause a magnetic field, and it will just exist. When the charge is not there, it's not moving, zero velocity, no magnetic field. It starts to move, and it will create a magnetic field pattern. And we'll discuss various kinds of magnetic field patterns based on different types of motion. But yeah, and collectively, all the charges together will add their fields. Magnetic fields abide by superposition, just like electric fields, electrostatic fields. And you get a magnetic field. That's one way. Another way is rotational motion. Rotational motion will cause a magnetic field as well. So a charge is just minding its business, not translating, not rotating, not vibrating. And let's say you could go up and spin it like a spinning top. What you would then see is a magnetic field would appear. And if you could see it, it would look something like the magnetic field of the Earth. And there's a specific North Pole and South Pole that it would have, similar to the Earth, based on the orientation of the rotation. And finally, the other kind of basic motion that we have discussed in mechanics was vibration. And if you take an electric charge and shake it, so that's the visual. Just shake it back and forth so that it has oscillation at a certain frequency. Not only does it generate a magnetic field, it already has an electric field, right? Because it's a charge, and we know what the field of a point charge looks like. But if you shake it, then you're essentially changing the flux, the electrostatic flux, and you're also creating a magnetic field that's not only there, but is also changing as well. And so the changing flux of the electrostatic field and the magnetic field that's generated because of motion essentially causes an electromagnetic wave, which we're actually using right now to operate the Zoom software. So the bottom line, when someone asks you that question in the future, the most straightforward answer that you can give is that anytime a magnetic field is generated, is created, anytime a charge moves. And that is translational motion. So anytime a charge translates, rotates, or oscillates. And this generates actually EM waves, the oscillation. And these will generate certain types of what we call magnetostatic field, where it's magnetic fields that are not changing. Magnetostatic, just like electrostatic. And but these are not static, they're waves, and they're combined with the they are associated with the electric fields. There's a whole physics behind that we'll discuss. And, just, I guess, a little picture, I guess we could have. In fact, maybe I should put it like this. Put a little picture under each of them. If I had a current wire, it's a pattern. So it's kind of hard to draw, but let's just say we have a wire that has current in it in some direction. We'll just have a snapshot of that wire. And the current is running along from left to right. Then the magnetic field lines would look like concentric circles around the charge, around the wire, something like this. And as you go out, the lines would get farther and farther apart. if you are looking straight onto the wire, so yeah, if you were looking straight onto the wire, that say the wire is like this. So you know the notation that we're talking about, where a dot means something is coming out of the board, and a circle and a cross means something is going into the board. So like for the current coming out of the board, well, that's the wire, the magnetic field, so that's I. The magnetic field, again, there will be concentric circles around the wire, and they will be kind of close together when you get close to the wire, but as you move away, the lines will get farther and farther apart, like that. And they would have a specific orientation. For this wire, the magnetic field direction would be counterclockwise. So that would be the direction in which the field points as it goes around. Here, it would be kind of like this, like that. For a current, for facing it going into the board, the orientation would just simply be the opposite direction. So into the board, still have the concentric circles, but the orientation is the opposite direction. And we'll discuss why that is and everything as we move along. Yeah, so that's translational motion. And essentially, and again, that's the collection of all of the small magnetic fields of all the charge of the wire. They would group together and give a field that looked kind of like that. Rotation. In fact, in quantum mechanics next semester, we'll study that at the end of the chapter. At the end of the course, kind of get into a little bit of quantum mechanics. And you may know, so if you've had chemistry or advanced chemistry, you would have confronted a little bit there, that the way that your particles are organized in an atom, they have what we call quantum numbers. One of those quantum numbers is called spin. Spin is associated with the magnetic field of the charge because it's spinning and it creates a magnetic field. Now, when we represent that, we just kind of represent it with the North Pole. Like if you see it, at least in physics, I don't know what they do in chemistry, but you might see the spin of usually use, what we will derive something called a magnetic moment, which is very similar to, well, it's analogous to an electric dipole moment, which we talked about. But the symbol we use for magnetic moment is mu, so mu b. And it's a vector and it has a certain direction, and that direction is the direction of the magnet of, I guess, would be consistent with what would be the north pole of the charge. So this would be the case, say, if the charge, because it depends on orientation. So the charge would have to be spinning. If you're looking down on the top, it would be spinning in the counterclockwise direction. So I guess the way that I would represent that here is maybe put like a little curly arrow to tell the direction of the spin. So it would be something like this in that orientation. You can see that. And but what it's actually representing is, again, if you could see the magnetic field lines associated with it, it would look like the magnetic field lines of the Earth. So north means that the field lines are coming out of the thing and going in the other side. So again, that's kind of cumbersome. So you don't see it dramatized, illustrated like that in books. You just see the arrow that I just created. But that's what it's implying, is the field lines would look like that if you could see them. Let's make this red. So the magnetic moment is pointing out in that direction. That's mu. And that means that the magnetic field lines are pointing, coming out in that direction and going back in the other direction. So we just draw the magnetic moment, so we don't have to draw all these arrows like this, but that's what it means. Yeah. And so the reason that all material, all the atoms, both positive and negative charge in material are magnetized like that. But the thing is, if you were to have a look at the magnetic fields for most objects, for most materials, they have arbitrary direction and they're vibrating all the time, so they're never going to line up. So within a material, maybe all the magnetic moments, these are the charged particles, atoms, everything, they all have arbitrary magnetic moments. And so they kind of all cancel everything out. So they might just be pointing in just very arbitrary directions, and so they don't add up. But the way that you can magnetize certain materials, like a paper clip, for example, we've seen that, where I could take a paper clip. So this is a little magnet here, and put it on the magnet. Then for a little while, after a while, depending on how strong the magnet is, if I take the paper clip away, then the paper clip might be slightly magnetized. That's because if you apply an external field, a very strong external field to a scenario, so this is just some arbitrary metal right here that is non-magnetic, but some external field is applied to that, so maybe the field goes through the thing, like this. Put some black in there at some point. A very strong blue. But maybe the field goes through, the external magnetic field goes through like that. And we use the symbol B for magnetic field. E for electric field, B for magnetic field. I don't know the history on that. I don't know why it's B. But anyway, so what happens is the magnetic moments can be affected. Magnetic moments of the individual charges can be affected, and they will slightly turn, right? Just like a compass needle, right? You put a compass needle and it turns to show you north. So these will act like that. And they'll kind of turn. Now, they don't turn all the way around like a compass needle, but just a slight variation in the direction of the external field will give components of the individual magnetic moments that can add together to line up in that direction. And they'll stay like that, after a while, depending on the strength of the external field. And that's why it can be magnetized for some period of time afterwards. But as we know, there's always vibrational kinetic energy associated with the particles. So over time, that vibrational kinetic energy will kind of take charge and then reorient the individual magnetic moments back to their original positions or whatever position they had, where the component then would go back to zero because everything is canceling out. And so that's how that works. Yeah. And finally, as I said, the vibrational motion. Now, and the same thing with the vibration here, because they're all vibrating. But again, they're creating, I guess, what you would consider electromagnetic fields that are kind of coming out, electromagnetic waves, but they're all canceling out one another. So it's, there's no collective. But if you had a controlled charged particle that you vibrated, as I said, it would create an electromagnetic wave that will pulse out. And this is the way you probably want to think about it. This is how I think about it. So oscillation, this is just a model that I like that seems to work very, very well with explaining to students. Let's say that we have a charged particle somewhere out in space. And if I have a charged particle, we already know that it has an electric field. And the electric field goes out, like this in all directions. basically out to infinity. But if I spin the thing so that it has a magnetic moment, then I can represent the magnetic moment with the magnetic field that's maybe doing something like that, right? So that's mu B. These are the electric field lines E. But now I have magnetic field lines that are also that look like this, right? So here, maybe those field lines. Now it's going to be hard to draw, but there's one thing that is true about electric and magnetic fields whenever they're coming from the same object like this, that everywhere that a magnetic field line crosses an electric field line, it will do so at a right angle. So I know the magnetic field lines are kind of coming out like this, but every place it would be at a right angle to the electric field where it crosses, like right angle to the tangent. But it will still have that kind of orientation thing like that. So the way I kind of think of it in my mind, but they wouldn't be circles. They would be the field lines that look like the standard bar magnet that I think it was Dami, whoever was talking about. No, Daniel, whoever said that earlier. But still, you have that kind of relationship. It's really interesting if you could see them. And they had their orientation. They're spinning around like that, and the magnetic field coming out of the board, so they would have a direction orientation like so. But if you could think about it, it would kind of, if you could see it, they would form kind of like a web, kind of like a spider web. And you know how spider webs, how they have, with the spider web, you have the lines going out, but you also have lines connecting them kind of like that. Now, they don't do 90-degree angles. You can see that how I'm showing here, it's not really a 90-degree angle, but they are connected like that, right? Something like that. Well, and this is a two-dimensional representation. Here, I was trying to draw a three-dimensional representation, but I guess that's also 2D. But the magnetic field lines and the electric field lines would form a kind of the static fields. Is what we're talking about. The static fields would form a kind of pattern like that, and that pattern would go all the way out to infinity. If you could see it, it would be three-dimensional, like a three-dimensional spider web going all the way out to infinity. And these are the static fields. So, meaning that the fields themselves are not moving; they're just static, like a static, just field pattern. And it would go all the way out, and at infinity, it would go to zero. Now, if I came along and I shook that charge, you can imagine whenever you see a spider web, if you take a little rock or a stick or something and poke it somewhere, then that creates an oscillation in the middle of the spider web pattern that would just propagate out, just like if you dropped a stone in a puddle of water, right? The wave would propagate out on the water. We know what that looks like. Well, that would happen somewhat to a spider web. But if I shook this charge, the same thing would happen on the static field, the magneto and electrostatic field pattern. It would just propagate out all the way to infinity. It would have certain properties, frequency, and it would be, it still would maintain its what we call orthogonal relationship, where there's 90-degree. Basically, there's several models that you can illustrate this. One model that we illustrate, which is different than the model I've given here, is if the red is the magnetic field, the direction of the magnetic field, and the purple is the direction of the electric field. Basically, you could represent the direction of the field as oscillating back and forth, the electric field doing that as it propagates in the direction of its velocity, and the magnetic field oscillating back and forth. So what you would get is something like this propagating out, in space, where the directions of the field is perpendicular to the direction of the motion of the waves. So that's one model that we'll look at. But this also is a really intuitive model that I like to build. You're not going to see this in the physics book anywhere. This is just my own creation. But that's really what's happening when you're shaking a field. shaking a charge, is that those static fields begin to vibrate in a way that that vibration would propagate out as you move away from the field. And they're electrostatic, so you wouldn't get much attenuation, not in space. You'd only get attenuation, and in fact, the field would only die down if it moved through things that had other charges, like moved through, dust or gas in space, or moved through a star. The interaction of that field with the magnetic field of that star or that planet, or charged particles, it could kind of distort the energy or take the energy away, and that's what would maybe distort the power of the electric field. But that's essentially what an electromagnetic wave is. So these are, from an intuitive point of view, these are all the different types of of magnetic fields and electromagnetic fields that we discussed. So when we're getting a signal from a satellite, or the signal that you're receiving now from Zoom, it's a pattern like this. Somewhere there's some electric charge vibrating in such a way that creates a specific signal that we can turn into sound, or we can turn into a visual picture, a representation. But in any electromagnetic wave, the radio on your car radio, the remote control of the lock of your car, or the remote control of a television, somewhere this is what's happening to generate that electromagnetic wave. And we know there's 7 electromagnetic waves that we have identified, types, and they're just distinguished between what we'll call frequency and wavelength, which we discussed that a little bit in oscillations, but not much. But that's also Physics 39, where we go more comprehensively in different types of waves, and we'll discuss the mechanics of a wave, and so we'll do that later on for E&M, for electromagnetic waves, later on this semester. But that's it. That's how a wave is. That's what magnetic fields are. That's how they're created. Any questions about that? Kind of interesting, huh? I find it to be very fascinating that that's the reality of what happens. Well, generally we start off by talking and defining what magnetic force is. And once we define magnetic force, we can use that to give a general quantitative definition of the magnetic field. So let's start by doing magnetic force. So I had a couple other things here. Oh, good. For the introduction, what do we have? Yeah, but there are bar magnets that exist. The bar magnets are created in the way that I said here. Like bar magnets are created with the same kind of philosophy as what I was describing with like a paperclip. But what happens is molten magma somewhere down in the earth, when magnetite, for example, is forming, and it's molten, it's much more, it hasn't solidified or crystallized into its crystalline structure. So the charged particles are in the molten magma, and they're much more malleable. So, and they're down in the earth, and in the earth, the magnetic field is stronger. You can see, as I said, the same thing that we have with the electrostatic field lines, that wherever the density of the field lines in space is higher, that means the field strength is higher. So just looking at these electric field patterns I've drawn, you see that as you get closer to the current wire, for example, the density of the lines is higher, which means the magnetic field is stronger there. Well, clearly in the earth, inside the earth, right, you can see that the field lines are all bunching up together as opposed to outside. And the magnetic field is pretty strong on the outside. It protects us from the sun and the solar wind and all this. So if it's that strong on the outside to be able to protect us and keep us alive, you know it's strong on the inside, like incredibly strong. We don't even really know, honestly. I honestly don't believe that we actually understand how the magnetic field is created. That tells you just how um, how complex the magnetic field is inside the Earth. In fact, I won't get into that here in this lecture, this class, but I'm kind of into the. Does anyone subscribe to the television network Gaia, Gaia, or have heard of Gaia? Anyone? No, no one's heard of Gaia. Well, it's a network kind of like just any like Netflix or anything like it's a streaming network. But it's more for it's kind of talks about a lot of maybe metaphysics, which is some people consider pseudoscience. But some of the programs, they look at all kinds of like archaeological and historical aspects of the earth. I mean, Gaia actually is a word that means earth. I think it comes from Latin or something. And a lot of shows like Ancient Aliens, and if you have ever seen that or know about that, these kinds of shows are on that network. But they also have a show called Cosmic Disclosure. A lot of the different shows are very much related in terms of the history, the archaeological history of the earth, and there's there's a whole lot of conspiracy theories that kind of been floating around for years, but one of them is this idea of that the earth in some way is not necessarily hollow, but there are, and this is actually, I think this is actually definitely documented, that there are large caverns inside the earth. Large caverns. I mean, we've seen these in places like you can go online and see, like in places like India, and in the forests, the Amazon forest, where there's, you go into a hole and it opens up and it turns out to be a space somewhere inside a cave that's, like the size of New York or something like that. But that's still very somewhat near the surface of the earth. But what people say is that the earth, even several miles down, like 5 to 10, 15 miles down, that the earth itself is more like kind of a honeycomb, all like very deep into the earth, not just, on like into the mantle, not just into the crust, that is honeycomb even into the mantle. And just very interesting phenomena that we say that people say, and some of these people say is there that we know about, but just don't publish or it's not mainstream, but that is actually, there's a much larger complexity to inside the earth than what is taught in mainstream science. So I thought that was just an interesting point since we're talking about, but that the magnetic fields are extremely strong and all kinds of things are going down inside the earth that that is not necessarily talked about in mainstream science. But anyway, the magnetite is formed, as I was saying, the magnetic fields are so strong that they can cause these magnetic moments to completely align while the material is soft before it solidifies. And when it does solidify, all the magnetic moments are in the same direction. So if you would kind of see inside a bar magnet, you've got all these magnetic moments that are just aligning, right? And so they'll create a magnetic field that is very strong and basically is permanent. Right? So magnetite might look something more like this, where the magnetic moments are just straight up aligned like that, right? So then the magnetic field then, is permanently fixed in the wire. And I think the other thing, I think I mentioned this, but one big difference between magnetic field lines and electric field lines is that there is no beginning or end with magnetic field lines. They're connected. So there, we don't, in electrostatics, we say that we have the electrostatic monopoles, where the electric field actually begins on a positive charge and ends on a negative charge. But for magnetic field lines, there are no magnetic monopoles. And therefore, we will, we don't have a source. So the magnetic field lines just are continuous. They do not have a source. But what I was illustrating here is that, yes, this would be considered the south pole of the bar magnet, where the field lines go into the bottom, run into the bottom, and the north pole of the magnet would be considered where the magnetic field lines come out of the bar magnet. So we don't illustrate a bar magnetic moment a bar magnet with magnetic moments like we do the charge, like we do with individual charges. But essentially, that overall magnetic field is coming from the magnetic moments of the individual charges that have aligned inside, inside the object. So this would be like kind of what magnetite would look like, which is, is a metal that naturally forms a bar magnet inside the Earth, and this is how it does that. So I said something kind of important that we should list as a property. A couple of things: that magnetic field lines are continuous. Just some basic properties we could say. I've kind of described how bar magnets are formed, and we can say that magnetic field lines are continuous. Oh man, these things. Like markers are not working. Only the ink. Continuous. And there are no magnetic monopoles that we have found. Yeah. You still have the idea for bar magnets, like poles repel and unlike poles attract. Bar magnets do possess north and south. And you can say that like poles repel, unlike poles attract. And finally, I would like to say something about the Earth. Right, so the Earth's magnetic field, Gaia, since I mentioned that, we'll just put that word there. Gaia is a word for Mother Earth. Sorry, folks, I gotta, sorry. Excuse me. All right, folks. Handle some family business in the age of COVID. Gaia, Earth, yeah. So, yeah. So if we draw the like a picture of the Earth here, beautiful Mother Earth. Do something. Forgive my lack of artistic skills. Looks like I don't know. Something like that. Let's see. Well, we know that there is a geographic North and South Pole, right? So the geographic North and South Pole is gonna, let's say it's straight up. And we know it's tilted, but like, let's say it's straight up. Well, it's tilted. So say if it's something like this. So geographic North, so I'll say geographic North and geographic South Pole. Well, it turns out a couple things about the Earth's magnetic field. One, it's not aligned with the geographic North and South. There is something called an angle of declination. Right now, it's somewhere between 11 and 12 degrees, I think, but it actually is moving. People think that we're in the midst of a pole shift. That's actually something that you read some places people say that doesn't exist, but that's not true. It does exist. It's right now, it should have been proven that every couple 250,000 years or something like that, when in the past we think something that the magnetic poles of the Earth shifts. And right now, it's about 11 degrees, so it'd be more something like this situation here, where the magnetic north. So, and that the other thing. So there's an angle, and that angle is approximately 12 degrees. It's called the angle of declination. So we'll say approximately 11 degrees or so, 12 degrees. But the other thing is that up in the region of the geographic North Pole is the magnetic South Pole. And down here at the geographic South Pole is the magnetic North Pole. I don't know if people knew that or not. But so it's almost, you can think of it like this. It's like there's an upside down bar magnet that goes through the center of the Earth at an angle which is about 11 degrees relative to the geographic North and South Pole. So here we will have the South Pole here up at the geographic North, and the North Pole at the North Magnetic Pole at the geographic South. And that angle, as I said, is called the angle of declination. Declination angle. $11 degrees. Okay, so that completes our introduction to magnetism. What do you think about that? Pretty fascinating, I think, magnetism. Any comments, questions, or observations anybody want to make about their experience with magnetism while I change the ink on my markers. Nobody? Anybody play with bar magnets when you were a kid? I was fascinated with them actually. Sorry. No one? Magnetism, I think it's really our ability to exploit and control magnetism has been quite significant in the advancement of our lives. Quite significant. No comments?
Is there a reason like why magnetic north and geographic north are different sides?
What do you mean?
Like it's a direction, like it's magnetic southward, and yeah, geographical
Well-
north. Yeah, it's like
Well, I guess I would say that, you know, one reason is because of the orientation of the field lines. And as I've drawn, we define the North Pole. You know, first of all, the lines are continuous, okay? So if you have continuous lines, that implies that you'd have to have, you know, that's coming from a source, like the picture of the bar magnet here, then you've got to have some way of distinguishing that the directions of the magnetic field line relative to the bar magnet is different at one side versus the other. So that's one thing, right?
my
Here,
question is like, why is the geographical north it's there? Like, why is it not geographical south? Like, why wouldn't you just consider magnetic north for like, you know what I'm saying? Like, it's, I understand that part, but I'm just asking why not? Why didn't we? I don't think it's a physics question. I don't know why if it's geographical north.
actually, I think I do understand the question, and I'm answering it. I think there's a subtlety
Okay.
here that you're not catching. Let me do it a different way.
Okay.
Let me answer a different way. Let me draw this picture a different way. And this is the picture of it. So when we get to something called induction, I'm going to take that picture right there and do kind of a modification where we think of the magnetic field line as straws coming out of, so they're always connected, right? They're not going to be independent lines, but for the purpose of some physical properties like induction, it's not necessary to think of the whole connected pattern. So one of the things that I do when we're talking about magnetic flux, this is a couple chapters away, but if you know, like if you go to the fair, sometimes you can get those big fries or something and they stick out, you know, like a bunch of fries and they're in a cup and they stick out of the cup, right? You know that picture, like straws or something? Yeah.
Right.
So if I were to look at the top of this bar magnet, right? So we know the field lines are doing this thing that I said, right? We know they're coming out of the top and going into the bottom like that. But if I were to, you know, and it goes all the way out to infinity, kind of like that, right? Coming out like this. But if I were to cut off everything else and just look at the tops of the field lines coming out, right? They're going to look like this. They're going to look like straws just sticking out, you know, of the magnetic field of the top of the and this would be the North Pole, let's say. So they'll look kind of like straws of sticking out of the top of this metal bar. You get that? Get that for now? You know? Yeah, okay. So what I'm trying to say is that if you look at this part, the straws are coming, they're pointing out because they have a direction. But if you look down at the bottom, the South Pole, and drew the straws in the same way, they're still going to be coming, you know, like pointing with a kind of, or they're still going to be looking like straws coming out, but they're pointing in a different direction. They're going to be pointing in.
Right.
So there's got to be some way of distinguishing between that difference relative to the bar magnet. That's what I'm saying. You know, there's some difference here. In one side, the magnetic field is pointing out, and the other side, the magnetic field is pointing in.
Right.
So that's the first thing to acknowledge, that there's a difference. So how do you acknowledge that difference? You got to do it some way. I think they just called them two different things. And maybe your question is, why isn't this north and that south? Well, I don't know. You know, maybe out is, I think it's more associated with the right-hand rule. I think just the way it has to do with but even then, it's still going to be an arbitrary name of why you called one the north and why you didn't call the other thing north. But my point is that what we'll see is that, as I told you, these magnetic moments are associated, these magnetic field lines are associated with magnetic moments. So inside, it means that the charges are, if you look down on them, they're rotating in the counterclockwise direction. And that's associated with something called the right-hand rule. So if a charge is rotating in a particular direction, you curl your fingers in the direction of rotation, and that points in the direction of the magnetic moment. And the direction of the magnetic moment is consistent with what we call north when you put all of them together and consider the overall field pattern. So I guess I would answer your question in a twofold manner. First of all, we've got to have a distinction between, on a bar magnet, between one direction and the other. Why? Because the direction of the field is different relative to the bar at one side versus the other. Now, once you make that distinction, you got to name it something, and the names have to be different. So I don't know, maybe it was just arbitrary that they called the field lines coming out north and the field lines going in south. Sure, you could have done it the other way, but even if you had done it the other way, you could still ask a question and the answer would be the same. You got to have a distinction. So that distinction is north and south. And, you know, maybe beyond that is arbitrary why they call the thing coming out north as opposed to calling the thing coming out south. It's because of compasses.
Yeah, I was thinking about that, like it's going in that direction, right? As you said.
But what I'm trying to say is that's the way the compass needles are named. Like it's because compass is the north side of the magnet points to the north and the south. But what I'm saying, that's the same answer. Why you could go back to the earth. Why is, you know, you could say it's north seeking, but that doesn't really even make sense. It's north, but the top of the earth is the south magnetic pole.
Yeah, that's what I'm saying. Like, it's direction, as you said, it's going in that direction.
You still, I think you're missing my point. The direction, first of all, even geographic north and south, you could make the same argument. Why is the top of the earth? It's not even the top of the earth. We're just calling it that because that's how we chose to call it. There's no top and bottom when you think of the universe. You know what I mean? Like, it's kind of like when I tell you that when you assign a coordinate axis to something, the physical thing doesn't know what you're calling positive and negative. So it's arbitrary. But once you define it that way, then everybody has to use it that way. Otherwise, you don't know what you're talking about. Well, the earth is the same thing. There's no inherent North Pole, geographic or magnetic. We're just calling it that because we have to all decide to call it something. So then once you establish that and then you say other things are called that, okay, fine. Yeah, that's true. Maybe we are saying this is north because it's pointing to geographic north, but it's all arbitrary. So there's no physical reason why, because that's what I thought you were asking me. What is the physical reason why? Well, it's arbitrary. That's my point.
Right.
Yeah. But the reason that there is a north and south, that you have to say something about it at all, is because there's a difference in the way that field line is interacting with its source, the bar, as opposed to the other side. Once you make that distinction, what you call it matches what you called other things. But that's not the physical reason why you would have to call it something in the first place. The physical reason is because there is a difference relative to the source that it's coming from. That's the way I would answer that. Yeah. Yeah. And going back to that compass needle thing, by the way, yeah, it's yeah, that's really interesting because you know, this idea, it's consistent, you know, for a compass needle, it's consistent with the idea that like poles repel and unlike poles attract. So it's true that the North Pole on the compass needle is pointing to the geographic north, but that's because at the top of the Earth, it's attracted to a magnetic South Pole. I just want to reemphasize that. So yeah, it's a little bit counterintuitive when you think about it in terms of just strictly magnetic poles as opposed to geographic versus magnetic. Yeah. Well, yeah, you know, I guess you could answer that a couple of different ways. Really just depends on your perspective, but
So since they're moving, they should align at some point, right? As you said,
what should align?
the magnetic north and the true north, geographical north.
Actually, they're moving away from one another right now.
Oh,
But
okay.
yes, the answer to your question is at some point it's conceivable that they were aligned, but they're moving, it's moving in the opposite direction. So it's going away from the north. But yeah, at some point I think you were right. They conceivably could be aligned. That's true.
Okay.
Anybody been keeping up with this thing in about Antarctica? You know, talking about the middle Earth or hole in the Earth. You know, people say there's a big old hole up in the north, the Antarctic pole. And do you know that? And this is a true fact. And I'm not going to get into conspiracy theories, but this is a true fact that once you join the United Nations, you have to sign an agreement that no country that is part of the United Nations, you can't just go to Antarctica. Anyone know that? No one can just go. Anyone, not an individual, not a country, anything. You just can't go down there because there's a bunch of crazy stuff down there. They say. Has anyone ever heard that before?
No.
But yeah, you can look it up. You can't just go to Antarctica. And also because of the global warming, you know, stuff is melting. And some people say that there's I don't even want to. I just let you look it up. I don't want to get conspiracy theory, as I said, but the ice caps are melting, and they're finding stuff down there that is inconsistent with the historical what we have been taught is the history of civilization on the earth. So Google it and you'll see some of the things I'm talking about. And as the ice caps are melting, this is pretty, people don't talk about it much, but you can see it, it's there. Things are, at some point, I guess there's gonna have to be some sort of acknowledgement by science, but right now people are still kind of sitting on top of it. But I think it's pretty consistent now. I mean, these rumors have been going on for years and years, but I think because of the global warming and the fact that it's going to be pretty obvious at some point that people are going to have to start talking about it. It's pretty interesting, fascinating. Yes. So let's move on and try to quantify some of this stuff. So we'll start off by talking about magnetic force, and we simply just write down it. It's an empirical relationship. When you look at charged particles moving in a magnetic field. Force on a magnetic charge. We'll start off by talking about that. Now, I just talked to you about what causes a magnetic field. So this section is magnetic force on a moving charge. What is wrong with these? I just filled this thing up. Now, I just talked to you about, where what causes magnetic fields, and we just said that a moving charge creates a magnetic field. But let's now consider an external magnetic field that's caused by, I don't know, something, like the Earth has an external magnetic field. But in the lab, we can create magnetic fields with specific orientations. What we will see is that if you have some magnetic field created somewhere in space, so let's say that we've got a field pattern in which a field pattern. Now, when we did something like electrostatic field, we said you can create a field pattern in a capacitor plate by aligning charges up and everything. Well, there are places where we don't have magnetic monopoles, as I said, but still, you could create regions in where the magnetic field, at least even if not physically, it's difficult to talk about, but theoretically, you could do that, where the field is constant. So the magnetic field pattern, they look like straight lines. In fact, if you were to go to the Earth, right, I've taken the picture off, but close to the equator, the lines look like they are kind of parallel. We know they're not because of the curved pattern, but because, closer to the poles where the field lines are going in, that's where the fields change very rapidly. And things like the aurora borealis are created by the fact that the magnetic fields at the north and south pole, not only are they stronger, but they're changing more rapidly per unit volume of air, or within the space, because they're curving more in order to go into the Earth. Likewise, farther away from the poles, basically near the equator, the magnetic fields change less. And if you were to see them, they would probably start to approximate parallel lines, because they're not, the flux is much less because the field lines aren't changing as much per unit volume of space. So that's what I'm trying to get you to visualize, that let's say theoretically in some place, we can consider that the magnetic field is constant and that it's not changing. Okay. Now, so that's what this is supposed to represent, a constant magnetic field pattern. That they can exist, at least theoretically or approximately. Okay. Now let's consider a field pattern in some region where the magnetic field is constant, but is coming out of the board toward us. So the way I would represent that is a field pattern where, I'm using the dot and cross notation for in and out, but we're looking straight on, and the field pattern, it would look like straight lines, but because I'm looking straight on, it's coming out toward me. And so anytime you see, some sort of lattice of lines like this, where it seems to be consistent space between the lines, that implies a constant field. So this is a magnetic field pattern, and the magnetic field is coming out toward me. And it's created in whatever way, I don't know, we're not gonna, maybe it's, it could be any very number of ways in which we've created this constant field. Now, we've also said that whenever a charge is moving, it has its own magnetic field, which I've talked about, at length previously at the beginning of this lecture. But when we talk about the magnetic force on a moving charge, we're speaking of an external magnetic field that has nothing to do with the magnetic field of the moving charge. In fact, what we are implying is that we're not even considering the magnetic field of the moving charge at all, that it's so small that it is negligible compared to the magnetic field of the external magnetic field pattern within which it is moving. And so therefore, we're not considering that. So don't confuse that. Don't get that twisted, right? That although any moving charge creates a magnetic field, when we apply an external magnetic field, that external magnetic field has nothing to do with one, and two is usually much, much stronger than the magnetic field of the moving charge, such that the magnetic field of the moving charge is negligible and is not being considered. Okay, everybody got that? Okay, wonderful. So now let us consider this moving charge. This moving charge has charge and it has velocity. And it is moving. And let's say for the purpose, let's say that this external magnetic field, I have a switch and I could turn it on and off. And I happen to turn it on right when this charge, let's say it's a positive charge, is right in the middle of the vicinity in which this magnetic field would be operable or influence the area, the environment in which it would be exist. And so the charge has a drift velocity or a speed, let's say just v. It's not really a drift velocity because we usually refer to drift velocity as something within a it's just a velocity. Maybe it was accelerated by an electrostatic field. We've done problems like that where you cause it, whatever. We don't know. Like it got, maybe it was an electron gun and it got shot into some region where this magnetic field exists. We don't know, but it has a speed, a non-negligible speed, and its charge is Q. Okay. It turns out that when this charge interacts with this external magnetic field, there will be a force that will be created. And you might say, why? Well, there's no justification. I mean, the only justification is that in this universe, that's what happens. There's some questions like the kid keeps asking why, where at some point, that's just, the parent says that's just the way it is. There's some basic things like that. Gravity. Why does gravity make an object fall down? Well, that's just the way it is. There's no theory about that. Everything is based on empirical, the universal law of gravity is an empirical relationship, and you have to start somewhere. Gravity is an attractive force. Why? Because it is. Magnetic field force is created in association with a moving charge. Why? Because that's what we observe. That's the starting point. And once you start there, you build from there. That's one of these basic fundamental principles of the way things happen in this universe. Now, in the multiverse theory, which is becoming very popular in quantum mechanics, the idea is that there are an infinite number of universes. And in these other universes, there are other rules. Maybe in some other universe, magnetic field does something else, or the force is different, or gravity is repelling. I don't know, like how that would work. It seems like the whole thing would blow up, but I don't know. Like there's just an infinite number of characteristics, and some people say in all different universes, there's infinite combinations of the characteristics of physicality. And in this universe, this is the way it is. So that's one of those things. Okay. Now, what is the nature of this force? Well, first of all, let's write down the magnitude of the force. And from that, we were going to define the definition of magnetic field, and then we'll talk about the direction. So the magnitude of the force, the definition of magnetic field, and then the direction of the force. So empirically, if we have these three quantities, magnetic field, external magnetic field, charge, and speed, it turns out that the magnitude of the magnetic force is related to those things and is related to the angle between the velocity, the direction of the velocity, and the direction of the magnetic field. And by empirical observation, we find that the magnitude of that magnetic force, which I'm going to designate at F as F sub B, is equal to the magnitude of the charge times the magnitude of the speed times the magnitude of the external field times the sine of the angle between the direction of the velocity and the direction of the field. So where theta is the angle between V and B. That's it. That's the magnitude of the magnetostatic force, which is what it's called. Or well, I guess magnetic force. All right. Now, you remember in electrostatics, we did a similar thing. Coulomb's law is an empirical formula, same kind of argument. Why is it the way it is? It's just the way it is. And its nature, right? Coulomb force is K sub B, Q1, Q2, R squared, R hat. It's an empirical relationship. This is similar. But you also remember that Michael Faraday then used the force to define the general definition of a field. The E field was defined as F divided by Q. That was a definition. Remember, the reason was that sometimes it's nice to think of the force as coming from the field as blah, 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 all that stuff. Well, the same kind of thing is going to be done here. Now that we've established what the magnetic force is, we're going to use that to define essentially what a magnetic field is. That's technically where the definition of a magnetic field comes from. But it's a little bit more complicated, right? Obviously. And so here, what we say is that the definition of a magnetic field is the following. The definition of the field B, the magnetic field, is defined as, the magnitude anyway, is defined as three equal signs, magnetic force, FB, divided by Q, V, sine theta. But technically, this is the definition of the magnetic field. Now, that's kind of general, even though it probably doesn't look so general. I would say that this formula, this definition, is analogous to the definition of an electrostatic field. So it doesn't really tell you how, anytime you define something like that, this magnetic field, it's obviously not, I always remind you about empirical formulas. B does not depend inherently on, some velocity of some arbitrary charge that just happens to be moving through it. So you can't really use this formula to inherently calculate B for a particular phenomenon, but it still is used as the definition of the field. In other words, once we had this definition for different types of electric fields, like particular charges, we had to then use Coulomb's law to integrate, right? Like for a point charge, we then had to say E was equal to K sub E, uh, you know, uh, 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 Q. Well, in general, it was the integral of dq over r squared r hat, right? And so we had to then set that up and calculate what that field looks like. We're going to have something similar for B. It's called the Biot-Savart law, but it's next chapter. So you can't really use this to, to, in order to kind of get the functional form of what a magnetic field looks like, you have to use another equation. But this does define, in general, the magnetic field. The magnetic field relative to magnetic force. And yeah, so yeah, it's a little bit more complicated because you can't, like here, the way we got this is we just took Coulomb's law and plugged it into that. Here, you're defining this formula from this formula, so you can't just take this and plug it in that. You just get one, right? So it's not quite the same. So there is some differences in how we develop the formula for calculating magnetic fields, but still, technically speaking, I think in any credible physics book, you would see this as the definition of the magnetic field be associated with the magnetic force on a moving charge. That's all I'll say about that for now. The units for a magnetic field is something called Tesla, which obviously I think everybody knows who Tesla is. A genius physicist of the 1800s who was generally not given credit for being the magnificent genius that he was. Yeah, so units. Tesla are the, but we have a couple of different unit systems that we use. Tesla is basically MKS. So in general, MKS units, that's what we're going to use, a Tesla. And a Tesla, you can get the units directly from units here. We also have something called well, there's several ways that you can describe Tesla. You could describe it in terms of, what am I saying? It's just taken directly from here. This would be a Newton per Coulomb meter per second. Right? You can just get that directly from this guy, right? Combining those. But there's different ways which you could put this together. Like, in other words, I could also write this as a Coulomb per second meter, right? And a Coulomb per second meter would be an ampere, right? Coulomb, charge over time is current. So that's one way that you might see it. You can think about it, a Newton per ampere meter, where you've kind of just translated the 1/seconds in the denominator to be associated with the coulombs. But because a Newton is a kilogram meter per second squared, there's another way we can organize this, which has to do with, so Newton is a kilogram meter per second squared. So divided by, how do I want to do this? Yeah. So how do I do that? Just gentlemen, just a second. That one is a well, I'm overthinking it. I'm overthinking it. If I come here, just come straight down. If I multiply a Tesla by and its symbol is capital T, as you do with no hat. If I multiply Tesla by 1 in terms of meter squared over meter squared, then I could also write this, the units for a magnetic field as a Weber per meter squared. Weber, W-E-B-R per meter squared, where a Weber is equal to Tesla times its the symbol is W, WB, no, yeah, WB, right? WB meter squared. And a Weber is equal to a Tesla times a meter squared. And it's a unit for magnetic flux. Remember, we talked about electrostatic flux, which we defined, where there's something called magnetic flux as well. And it has units of Tesla times meter squared. So it's the flux of a magnetic field through a cross-sectional area. Cross-sectional area is meter squared. So a Weber is a Tesla meter squared. So sometimes you can define Tesla in terms of that just by, because obviously if a Weber is Tesla meter squared, you divide by meter squared, you're going to get a Tesla. So sometimes you'll see magnetic field written in terms of this unit, Weber per meter squared. And finally, if that wasn't enough, we have another unit system for magnetic field, which is called a Gauss. And a Gauss is 10 to the 4th, or 1 Tesla is 10 to the 4th Gauss. And that has to do with astronomers and astrophysicists use that unit system a lot when we're talking about magnetic fields up in space or the universe. So a Gauss is also a unit of measure for magnetic field. And this is the conversion relationship that 1 Tesla is equal to 10 to the 4th Gauss. So we got a lot of stuff going on there. Tesla, Gauss, Weber are the different units for magnetic field, but you can always describe those in terms of the base units, as I've tried to do this in the first step here. A lot of information there. All right. Any questions, problems, troubles, gripes? What time is it? Oh, we passed our break. Okay, this is a good time to break. So I'll break right now. When we come back, so I promised you, what was it? This segment of lecture was defining force, then field, and then I talked about we're going to go back. So these are just the magnitudes, but now we got to go back and talk about direction, the direction of the magnetic force. And that's really interesting. It's really fun. But probably we should take a little bit of break right now. And when we come back, we're going to have a more quantitative lecture where I'll introduce something called the right-hand rule associated with magnetism. Now, you should be somewhat familiar with the right-hand rule. If you had me, we did something that's going to look very similar to this when we looked at torque back in mechanics, if you have me from mechanics. But even if you didn't, that should be at least one of the lectures you remember from mechanics when you have to introduce your right-hand rule and different ways you can do that with torque would be the first time you'd have seen that in mechanics. Well, we've got something very similar that we're going to do with this rule. In fact, you can see it here that anytime you have two vectors multiplied by the sine of the angle between those vectors, You can describe that vector quantity as what type of product? Anybody?
Vector.
Cross.
Yes, a vector, but Dami, yeah, cross product, right? Cross product. That's what I'm looking for. So here I can represent, yeah, so that will give a vector. You're right, Jason, but you could also describe those the product of those vectors that give rise to that vector result as a cross product. And it turns out that I could then take this and describe the magnetic force in the following fashion: that FB is equal to Q times V cross V external. And so therefore, obviously, with the cross product, that introduces the right-hand rule, which will give you the specific direction associated with the magnetic force. So we'll talk about that when we come back. All right, so let's take a break and let's come back in a little bit of time. So let's come back take a little bit more than 15 minutes. Let's come back at the top of the hour at 10 o'clock. All right. Yeah, hear me? Sorry, it took a little bit longer. And got you going with these problems first. Well, right-hand rule. There's a couple ways that I teach that. And with this particular exercise, we will do something called run, wrap, point. The right-hand rule. RHR, so I refer to it. It's kind of a mnemonic. I guess it's not really a mnemonic, but it's more an application of the left hand, of the right hand, right hand rule for the cross product. That if you have two vectors, if you run your hand like an arrow parallel to the first vector, so I guess we could apply it to something like the first vector. Well, I don't know, maybe if you have a cross product, C is equal to A cross B. Let's do it in the context of this equation. So parallel to A, then wrap, that is, wrap your fingers parallel to B. Then your thumb will point in the direction of C. Point thumb parallel to C. So let's say that I have a vector. uh, A is coming out of the board. B is pointing to the right. Then in order to run my fingers, so take your hand, you place it parallel like an arrow toward A. So run your hand like an arrow toward A. Now, in the second part, you're going to have to reorient your hand because your fingers can only wrap one direction, right? So you essentially have 360-degree possibility for orienting your hand once you wrap it toward A. But B is pointing to the left, so I would have to orient my hand so that my palm is facing to the left. That way I can then curl my fingers so that they're pointing parallel to B. So my arm is still parallel to A, my fingers are parallel to B. Once I have that, then if I point my thumb gives me the direction of C. So run, wrap, point. Or you could say run, face, point if you want to think of facing your palm. Face only really applies when the angle is 90 degrees between A and B like it is here, but wrap is more general. So here, the direction of C would be up, straight up, because that's the direction my thumb would point. Now I'm going to give you a series of exercises where you can practice these things, but I'm going to make it specific to the magnetic force, the velocity, and the charge. Also, the other thing I should put in, if this is for a positive charge, but if you have a negative charge, then you have to flip. In the end, you have to flip your fingers to the opposite direction. So run, wrap, point, flip for a negative charge. So let me give you an example of what this is going to look like over here. So let's say that I have do this one. So this number one. So I'm going to have a positive charge. The positive charge, the velocity will be to the left, and the magnetic field will be straight down. Okay. So what would be the direction of and all of these problems, the question is, what is the direction of the magnetic force on that charge moving in that external field? So as an illustration of this first one, now I'm going to take my hand like an arrow and run it straight forward like an arrow in the direction of the velocity. Now I have to orient my hand 360-degree possibilities to get B, but one is down so that when I bend my fingers, they're parallel to B. And then I point my thumb. So in that scenario, the magnetic force on that charge in that instant is going to be into the board. And I would then represent FB in the following fashion. FB is, maybe you can put it here, into the board. And that's the notation for into the board. So I'm going to just write down a series of problems and have you go ahead and work on these. Positive charge, just like that. See? And of course, in all of these problems, the magnetic field is external. Okay, so I want you to go ahead and start working on these. Give you a few minutes, 10, 15 minutes or so, whatever. And I'm going to call on people to, everybody's, got to answer. So everyone will have to answer the thing. And yeah, so, and let me give you a couple more examples too. Let's see here. Hold on a second. Okay. Yeah, so go ahead and start working on those. Let's see if I can find a couple more. Well, we can do some of those ones I just said. So let's say that we have a magnetic field like this. That's B. And we've got a charge moving straight down. The velocity, make it a negative charge, and it's moving, its velocity is straight down. So with that guy, give the orientation of the field. or the force, I'm sorry. So go ahead and work on those, and then I'll be right back. Jason, you finished pretty early. You want to start with number 2, Jason? What is the direction of the magnetic force? And explain to the class how, and there are other ways you can do the right-hand rule. If you've learned the thing with your fingers or whatever, you can do that, but just have some explanation. So number 2.
It should be pointing down, straight down.
See, straight down. Oh, you want to explain that? How do you get that?
So if I point my hand in the direction of the velocity, and if I curl my fingers towards the direction of the magnetic field, then my thumb should be pointing down, and since it's a positive charge, that's the direction of the force.
Okay, do that one more time. One more time.
Towards the velocity, and then I curl my fingers towards the magnetic field, and then my thumb is pointing down. So
Okay, so let's take a look at something. I think Jason has his camera on so everyone can see that. Now, one thing I want to warn you about with the cross product, we know that the cross product is such that the resultant field has got to be 90 degrees relative to both vectors of the cross product. That's just the nature of the cross product. So in this particular example, V and B are clearly in the horizontal plane of the board.
okay.
So when you're pointing down like that, that's also a vector that's in the same plane. So there's something wrong with that.
Oh, so into the board then.
Into the board. There you go. There you go. It's going to be into the board. So again, if you run your fingers like an arrow in the direction of V, you have to orient. Like when you did that, you curl this way, but that's not parallel to B. In fact, that's perpendicular to B out of the board. So remember that the whole thing, like right now, my arm is parallel to V. You see that? Now I have a couple 360-degree possibilities, but there's only one possibility in which when I curl my fingers, they are parallel to B. In that scenario, when you have that done, then you point, and when you point, you get into the board. Okay? So yeah, FB here is into the board. Now again, there are other ways you can do that. Some people take their index finger, make it parallel to B, their middle finger parallel to B, and then their thumb points parallel to F, but it's awkward for me. But you can do that if you want. I don't really like that. It makes me feel funny. All right, so let's see, Lucy. I'm gonna try number 3.
Is it into the board as well?
Okay, well, you gotta be a little bit careful because
It's towards, I guess, towards myself. So my thumb will be pointing at me.
I'll tell you, this is a little tricky. It's a little bit of a trick question. But remember, go back to the cross product. The definition of the cross product is that it's the magnitude of both of the vectors times the sine of the angle between each vector. What is the angle between B and V for this problem? B is pointing directly to the right and V is pointing directly to the left. So the angle between them is how many degrees?
Is that 180, right?
It's 180. Yes, it's 180. And what is the sine of 180?
I don't remember.
So that you definitely want to remember. Anybody want to help her out?
0.
Yeah, sine of 180 is 0 degrees. So in this particular case, you don't get any force because of the orientation of the angle. So FB is actually 0 for this one. It doesn't have a direction because it doesn't have a magnitude. That's a little bit of a trick. So you gotta remember that as well. So FB for this guy is equal to 0. Okay, why don't you you got less than 10 people. So why don't you go ahead and try this one again, Luke, and give you another shot. Try number 4.
That would be. Oh Jesus.
So let me help you. Take your hand. Let's go through the steps. Take your hand like an arrow and run it so that it's parallel to V. Do that right now.
Mm-hmm. Oh, would it be towards me?
Okay, very good. But remember, it's a negative charge.
Yeah.
So then number 4 means you have to flip it. So when you flip, what's going to be the direction?
Towards the board, right?
Into the board. That's right. So run parallel to V, curl your fingers parallel to B, wrap, point out of the board, but then it's a negative charge. So flip into the board.
Mm.
So VFB is into the board for this guy. All right, Dami, why don't you take number 5? Dami, you there?
Yeah.
Okay, go for it.
Would it be out of the board?
Explain.
So if you orient your arm to parallel to V and wrap it in the direction of the magnetic force, it should be pointing towards you.
Can you turn on your camera real quick and let me see what you're doing?
Yeah. So like if V is parallel to your arm like this,
Yes.
and I think the magnetic force is pointing in this direction, like parallel to V, and then it points like towards you. I don't know if I'm orienting my arm the right way, but
When you say towards you, what do you mean?
like out
Toward who?
towards me. I mean,
Yeah.
so it's like out of the
towards
board. Yeah.
out of the board. There you go. You got it. Good. Yeah. So at first I thought you might have been using your left hand because you're not. But so V. Well, actually, no, I think you're right. Like the first thing you said was into the board. Did you?
No, I said out of the board.
Oh no, it's going to be so. You have this right, but you can't wrap like how are you? Your B is up here, so how are you? You have to like you had your hand down. You're going to have to turn your hand around so that you can make your fingers parallel to B, in that way. You know, like your hand only bends one way. So when you have your fingers like this, B is above you here. So you can't bend like that and get to B. You have to kind of turn here and bend up. You know what I mean?
Yeah.
So I would say that it's into the board. Now that does beg a bit of a question that, you know, I guess it's something I didn't say. These rules, this right-hand rule, is basically applies for angles between 0 and 180 degrees. So they're only for, you know, like this, I guess you could say, well, I could bend it all the way around somehow, but that's, you know, that's going to go more than 180 degrees when you do that. And these rules aren't set up that way. Like it's set up to be between 0 and 180. So that would imply that you would have to go this direction, not, you know, go clockwise as opposed to counterclockwise. So I would say that for that reason, this is going to be into the board. Hope that makes sense.
If you do the one with the finger, it's out too.
Really? So index finger in the direction of V, middle finger now has to point in the direction of B. And now index finger parallel to V, middle finger has to be have to orient it so that it's parallel to B, and my index finger still has to be parallel to B, so I have to do something like that. And then I point my thumb and I still get into the board. So they're still going to be consistent. You see that?
Yeah.
Yeah, so that's, yeah. All right.
Professor,
Okay, good.
Professor.
Daniel, yeah, you're up next. You got a question?
Okay, let me go for number 6. Then I still have a question.
Okay, go.
So number 6, I think is gonna be into the ball.
So tell me, go through the process.
Because if I'm pointing towards V, if my arm is towards V, my thumb is like pointing towards the ball.
Let me see. I gotta see. Can you turn your camera on and show me what you're doing? Because you skipped some steps there.
So it's gonna be this way. And my thumb is gonna be pointing like towards the ball.
Well, you only did one step. That's just the first step. You skipped the second step. The first step is that, right, I agree. You start this way, your arm is parallel to B. But now you have to wrap your fingers parallel to B. What is the direction of B?
B down, back?
No. This is a cross. The cross means that B is into the board.
Yeah.
Okay, so now orient your hand and then make your fingers parallel to B from this position. Put your hand up again like you had it.
This way.
Yeah. So that's V.
Yeah.
Now you have to orient your hand and bend your fingers so that they're parallel to B. How would you do that?
Down?
B is not down. B is into the board.
Oh. It's gonna be like, it's gonna go a little bit forward.
Take your hands up out there. I can't, you put it below the camera. Okay. No, there you go. Yeah.
So,
all right. Let me ask you something right now. Go ahead and bend your fingers right now. Go ahead and bend your fingers.
Bend like down?
Well, you can only bend them one way, so yeah, bend them down.
This way.
Okay, so now, and I'm gonna do that. Now I usually bend mine right at the back hinge. Not like that. I'm gonna bend it like, but now you see, you have to now reorient your hand so that those fingers are parallel to B. How would you do that? There you go. You got to turn it so that those fingers are now pointing into the board parallel to B. That's what the second step is. So now that you have that, now go to the third step and point your thumb. So that is the direction of the force.
Okay.
So if I were to draw it in, it's going to look something like this. So it's not into the board or out. It's actually parallel. It's in the plane of the board, but it's going to be perpendicular. And this is the answer, that FB is always going to be perpendicular to both V and B. So in this case, we can clearly see that it's perpendicular to V, but it's also perpendicular to B because B is into the board. So F is up like this, and B is into the board. So they also form a 90-degree angle. So that's one way to know that your initial answer couldn't have been right, because you said down or something like that. What did you say? You said into the board.
I said into the board, but like, I was pointing down because, I wanted to go for, B, but like, I guess I was wrong.
I see. Yeah. Well, down could have been a possibility. In fact, if it were negative, it wouldn't have been straight down, but it would have been like opposite this direction. but it could never have been into the board because then it would have been parallel to B, and that's never going to be the case. If you go back and look at all these examples, the end result, F is always parallel to both B and B. Now, B and B don't have to necessarily be parallel to one another. That's just an ideal case. In some of the cases, I made it like that. But in this example, you can see that the angle between B and B is not 90 degrees. But the angle between F and B is 90 degrees, and the angle between F and B is 90 degrees, and will always be the case because that's a property of the cross product. All right.
All right.
Professor, can you repeat what you just said again about it being 90 degrees and hit a point?
Yeah, you can go back. So I remember I didn't give you any problems on the cross product. I think they have it in chapter 1. You can go back and review that, whatever. I think it's chapter 1 in this. Go back and review cross product in that chapter. One of the properties, say again?
No, I have a question. Like, I wanted to ask a question about number 3.
Okay, so one of the properties of the cross product is that C is always going to be perpendicular to both A and B. And so that is a property of this concept as well, simply because it's defined by the cross product. Okay, so that, I think it was, who was asking you that? Was it Donald?
Donald, yeah. Thank you.
Yeah, good. Daniel, what's your question?
So for number 3,
yeah,
because the sine of 180 is 0, so there is no direction for that one, right?
Yeah, and because there's no magnitude, there's no magnetic force on it.
So what if for instance, let's say the sine of 180 is 1, just for instance. So does it mean like it's gonna have a direction like, you know, to the right or into the board or outside the board or something like that?
Well, yeah, let's go to question 4. That's what we don't have to make a hypothetical question. Like, just go to a problem where the sign is 1, and that's this scenario. Because I didn't ask you what the degree was, but you can see that it definitely looks like it's 90 degrees, right?
Yeah.
All right, so that's going to have a force, and you just do the same process. You know, V cross B is out of the board, but then it's negative, so it's into the board. So into the board, the FB is still perpendicular to both B and B. And the angle in this case is 90 degrees.
Okay, yeah.
All right.
Yeah.
Good stuff. Good stuff. Okay, who's next? Who hasn't gone yet? I think Angel was asking a question. So Angel, for this rule, does my palm always face me? No, not necessarily. It doesn't always face you. Why don't you try number 7, Angel? Number 7, thumb faces towards me. Okay, so V cross B. Yeah, it does, but remember it's a negative charge, so then you have to flip it. So it's going to be into the board, not out of the board for that. Yeah, so does that make you get that? So run, wrap, point is out of the board, but then negative, so into the board. So FB is into the board on this. Why don't you try another one? Why don't you try number 8 again? Yeah, so that's also a negative charge. So Angel, go ahead and try 8. Awesome, awesome, very good. Yes, it is down. B is out of the board. B cross B is up, but then it's negative, so it should be straight down. Very good. FB is straight down. Who hasn't gone? So AJ and Shora and Monica. So AJ, go for it. AJ, go for number 9 here.
Yeah, there is no force because it's 180 degrees.
Awesome. FB is 0. Very good. Shora, number 10.
I want to say that it's facing towards the board.
Awesome. B, cross B into the board. Very good. I think you're getting the hang of it. And Monica, you want to finish up this guy? Oh, Mushkan, I forgot you. So, yeah, I'll make up one for you. Go ahead, Monica. Do number 11.
Is it to the right, to the left?
So B, cross B is to the right, but then you have to flip it. So good job, to the left. Yes. So Mushkan, I'm so sorry. Let me make up one for you before we have to go.
Okay.
Let's see here. Let me think of a good one. Good one for you. Let's try. Let's make the magnetic field into the page. And let's make a positive charge. And let's make the positive charge going velocity straight up. So try that one.
Would it be going to the left?
To the left.
If
So
it's represent going into the page?
the magnetic field is going into the page. That's right. Can you show me? You mind turning on your camera? Let me see what you do.
Okay.
Yeah, go
So I
for it.
just put my hand up and then
Yeah.
in the page, and it's gonna be going left.
So B, cross, but the magnetic field, that's out of the page.
Oh, I thought you said into the page.
Oh, did I? Sorry. I'm sorry. I might have, but then I might have just like a moment. But
Okay.
this is, yeah, I think I had
That's fine, right?
Yeah. So, yeah. So V cross B is to the right. Very good. All right. Thank you so much. So everybody got it? Got that? Any questions about that? All right. Well, cool. I'm not going to keep you over right now. I don't want to go past class, but this lab thing, yeah, I will. Wow. Yeah, let me try to. I actually do have one made. It's not so. Yeah, I'll try to get that up for you this weekend, and this maybe tomorrow, by tomorrow, and so that you can go ahead and we can start doing these labs. The labs are pretty easy, so we still have time to make up as many labs as we need to do. But we do need to start maybe this weekend, so I'll get that going for you. I keep saying that, but sorry that I haven't done it so far. Oh, Abdul, did you not do one? And David Edwards, I can't. What happened? How did I miss you all?
No.
You didn't do one?
No, I didn't.
So do one. Do one right now. Do this one. And David Edwards, you too. So here you go. That's B. And let's say B, and it's a negative charge, and B is out of the board. So 12, 13. So Abdul, do that one. Coming right now.
And would be B out of the board, you said, right?
B is out of the board, yeah. This is B right here.
So my index probe there would be 0 to B. And B will be downward.
It's a negative charge though.
Oh, sorry, it'll be upward. Sorry.
Yeah, so it's like more, so V cross B is down, but then you flip.
Yeah.
So then FB is going to be kind of like, it's up, but it's not quite straight up. It's at an angle, right? So and remember, it's got, yeah, left. And so it's got to make a 90-degree angle with that guy. Okay, and David Edwards, and everybody else, I hope everyone else did one. So David, so do this one. So let's say V is into the board. The velocity is now, sorry, out of the board. Velocity is out of the board, and the magnetic field is, let's say, straight down. So do that one, David.
Okay.
You can turn your camera on and let me help you if you don't mind. Okay. Okay, so now your right hand, the V is out of the board. So make your hand so that it's pointing straight back toward you, I guess, out of the board.
Out of the board?
Out of the board, yes. So that's going to be like back toward the camera. So if I'm out of the board, I'm like this. Yeah, you got to stand up. So point away from yourself. There you go. That's right. But your hand is still pointing toward me. It's got to point away from me, right? There you go. That's out of the board because the board is back toward the camera. Now, B is pointing down. So you have to orient your hand and wrap your fingers so that they're parallel to pointing down. So point them down. Go ahead. Good. Now point your thumb. Awesome. What direction is that, dude?
Down.
No, what direction is your thumb?
Left.
Well,
Forward.
yeah. To the board is right, but yeah, if you're facing you, like if you turn your body around to the left, but remember we have to make it oriented to what's on the board, so it's to the right. But I think you do have it. Yeah, it's to the right. When you're facing the board, it's to the right. Yeah, good. Yeah, does that make sense? You want to do another one, David? You want to do another one?
Yeah.
So do this one. Let me make another real quick for you. So let's say that again, B. Let's make B into the board. So no, B B into the board, and let's make V straight down. Okay. So V is straight down and B is into the board. All right. So first, make your hand parallel to B. Now V is straight down, so it's got to be like this. Okay. And try not to have any bends in your hand, like don't do, like have the whole forearm and your hand straight down. Yeah, I know it's kind of funny. So now then point your fingers so that they're parallel to B. So you have to turn your hand around so that your fingers can point into the board like that. There you go. Now then, when you have that, point your thumb. What is that direction? Relative to the board. Yeah. Yeah, it's also to the right. Yeah, that's right. So you see, you can't really, like you have to do the thing. You can't look at it and tell. These are two different orientations of V and B, but they're both pointing to the right. V cross B is also to the right. So you have to master this right hand rule. You can't just look at it, and I can't anyway, look at it and tell, right? You have to go through the process. And these are both assuming they were positive charges, by the way. All right.
All right.
So you just got to practice this. There's no other way. You just got to practice. You got to practice. All right.
All right.
Good. So did everybody go? Who is the Zoom user there? Is that somebody? Who's that? I know it's somebody. Who is that?
That's you.
Oh, that's me? Really? Oh, my bad. Okay. All right. Cool. So AJ, you went, and Angel, everybody went. Okay, good. So any questions about anything?
No.
No.
All right. Well, say again.
I say no.
Okay, yeah. So okay, cool. Yeah, so it starts to get fun. I mean, it's a lot of work for this class, but the class is also very, very fun, I think. And you can probably tell by my energy, like we've done a lot of the hard work, which is kind of building. Remember how in the first part of the class I said that E&M is can be a little bit difficult because you don't have an intuition for things, and like you do when you come into mechanics. But at this point in the course, we've spent a lot of time, I've been talking about the Einstein model and reinforcing that and, picturing the fields and things like that. So we're like, you've been doing this for a month and a half, 2 months now. And I can feel that, so this is actually complex material, but all of you are grasping it. And what that means is that you have now developed an intuition for this type of stuff, right? So this is where it actually gets kind of fun because the concepts that we will be studying from now to the end of the course are truly intermediate. Like they're not trivial. They are more advanced concepts. But a lot of it is not necessarily advanced mathematically. It's conceptually. It's a little, but you have now both the mathematical background, I believe, and certain, I mean, you kind of had that coming into the class, but you definitely now have the sensibility to be able to kind of understand the material. So, but you got to stay on top of it, keep doing the homeworks. And I would also stress, not just the things that you get the grade on, but the homeworks in the back of the book, in the back of the chapter, they are more rigorous, I think, than those Wiley Plus homeworks, even though you got to do the Wiley Plus to get a grade, because the homeworks in the back of the book are more like the kind of examples I do in class, where it really kind of gets into both the subtlety, the left brain part, the right brain part, and working the mathematics justification and all of that. So keep doing all of those things so that you continue to get a good foundation for, an understanding for the course. Keep on top of it. Okay?
Okay.
All right. Very good. You got your homework and stuff, so start working on that, and have a good weekend. Be safe, and I will see you, I guess, on next Monday.
Thank you.
All right. Thank you so much.
Thank you, Professor.
Okay. Bye-bye.
So you're gonna be taking physics 3-9 on the summer, right? And it's 5 weeks, I believe.
Yeah, it's 5 weeks. It's during the summer. Yeah.
Yeah, I was gonna ask about that as well. So
Yeah. Go ahead.
Do you think like the 39 is like an intense class, especially if you're taking over the summer?
No, it's good. Like, are you taking any other classes over the summer?
No, I don't think so. No.
No. Look, you're going to be very well prepared for it. It is intense, but the thing is, it actually, I kind of like it a little bit better than the regular semesters because, particularly if you're not taking another class, you do physics all day long, right? The classes are 6 hours long, 4 days a week. So the way we do now, like I teach from 8 o'clock to 2 o'clock, and so you know my style now. So it's very comprehensive. I don't skip a thing. I work out all the everything. But what happens is it's so intense that becomes a good thing because you're thinking about physics literally all. You go 6 hours for a class, then you take maybe an hour and a half, 2 hour break, then you got to do your homework at night. Then 8 o'clock the next morning, you're back doing it again. So after about a week, you kind of get into the groove And you actually learn more, I think, during that class than you do during the regular semester. So everybody kind of gets into a groove, and I think the class ends up being better in a lot of ways than during the regular semester. And if you've gotten through the first 2 semesters, and particularly if you have had me, I'm it's the same teaching style and everything. So you definitely will be able to handle it. And it's actually kind of a fun course. It's really nice topics, and it's rigorous, but it's no more rigorous than the other 2. And if you're not doing anything else, then you'll be able to handle it. It's no, it's not I don't think it's super difficult, but I think it's good. Yeah. So you thinking about taking it?
Yeah.
Yeah, I would say this. If you want to do that, I would go ahead and sign up for it now, just to because sometimes if there's not a whole lot of people, and I haven't really had this for several years, but they'll cancel it well before, because well before it opens, and that sometimes people wait till the last day or so, the last weekend to sign up, and then and then you have to go back. It's hard to convince them that you had people. So I would go ahead and sign up for it, because you can always drop it if you don't want to take it,
Okay.
Yeah. So if you're thinking about taking it, go ahead and sign up right now.
Thank you.
All right.
All right, thank you.
Yep. So Abdul, you had a question?
Yeah, but some question about the class assignment I sent you the email for.
Say again.
The email I sent you about the assignment, class assignment.
Oh, sorry. Yeah, I didn't check. I was busy with stuff yesterday.
Yeah.
So let's see. What's the email? What are we doing with? What is it about now? Remind me. Oh, right. Yeah, there was some. Let's see here. The inbox. Oh, I forgot to handle that. Right. So.
Thank you so much.
Opening. Oh yeah, right. So these are. Oh wow, yes, a lot of assignments. Okay, so. Yeah, let me go through and do that.
No, it's because like our pandemic and everything. For my parents didn't really work, and my sister lost her job last year, so it was like really hard to have to do 2 full-time jobs.
Okay, cool.
I took like 2 physics class and calculus 3 without knowing that I would be doing 2 full-time jobs. It was like really tough. So I just quit my security one last week, so I could just focus more on this stuff. If you can, please.
All right, sure.
Yeah.
So Q1, Q2, Q3, Q4, homework 4, homework 5. Let me write this down. Okay, so some of these dates probably will coincide with stuff that we did before. So that stuff that's coming up. But go ahead and do your best and try to get in before. All right, so I'll open those right now for you, okay?
Thank you so much, but I really appreciate it. Thanks a lot.
All right, no worries.
Have a good one.
Yeah. Have a good one.
Thank you.
Yep. Just oh, Dami, you had a question?
Yeah, for the number 14 that you gave David, the one that's on the board. So can you explain one more time why it's to the right and not the left? Because if you okay, let me turn on my camera. So if you the velocity is towards the board. If you run your finger, your hand, your arm towards the board, and then you point downwards to towards the parallel. You wrap your fingers parallel to the magnetic field, and you point your thumb. Wouldn't you be pointing left?
It would, but the problem is that V is actually out of the board.
Oh.
Yeah, the dot is, think of it like an arrow. So this is like the point of an arrow. So if an arrow were coming out of the board, you would see the point.
Okay.
If the arrow is going into the board, you would see the feathers, which is what the cross is representing.
Okay.
So it sounds like you got it, but just got the process, but V is actually out of the board. So that's going to flip it around and be to the right.
Thank you.
All right.
Yeah.
Good?
Yeah.
All right. Cool. All right. Keep working.
Have a good
weekend. All right.
Yeah, you too.